Today we're going to talk about Hermitian operators. These are a special type of operators that are very important in quantum mechanics, as we'll see today when we get through it. So far, we've discussed operators in general and how operators act on kets to form another ket. And they act on kets from the left, right? So A acting on the ket psi equals some new ket phi. However, an operator cannot act on a ket from the right. They don't sort of commute that way, I guess. That operation is not really defined. It makes no sense. You can see this sort of explicitly in what's probably more familiar, our matrix representation, and the fact that the dimensionality of the matrix representing A and the ket don't really make sense. That operation can't be performed. However, operators can act on bras from the right. If you remember, the bra is just going to be the row vector, the complex with complex conjugate elements. So the bra corresponding to the state psi can be acted on by the operator A from the right, and it's just going to form a new bra. We'll call that eta. However, in general, the resulting bra may not be the one you expect, right? So if we have the operator A acting on the ket psi and forming some new ket phi, or if we have the bra representing psi being acted on by that same operator A from the right, forming a new bra eta, that eta does not necessarily correspond to the resulting ket phi, right? You can see this again in the matrix representation. If we have some general operator A acting on some ket, which is represented by this column vector, we get a column vector that looks like this. If we do the converse of that and take that same, the bra representing psi, which would just be this row vector now that's with the complex conjugate elements, and operate on it from the right with that same operator, we get this resulting row vector. Now, if you'll notice, in general, those two elements, if that eta bra was the corresponding bra to the ket phi, this would be true. This element of that column vector would be the complex conjugate, or this element of the row vector rather would be the complex conjugate of the column vector, and we just see for both of those elements that's not generally true. However, it is true in certain cases if those off-diagonal elements are actually complex conjugates of each other, and if the diagonal elements are essentially real, the complex equal to their own complex conjugates, this will be true. The resulting bra and ket will be corresponding to the same sort of answer. Another way of writing this is if A is equal to A dagger, i.e. if you take the transpose of the matrix representation of that operator and complex conjugate it, if those end up being equal, then we have that result is true. The operator acting on some ket gives us a new ket, and that operator acting on a corresponding bra gives a bra. The results are going to be the corresponding ket and bra. In our bra ket notation, this looks like this. You're basically just writing that complex transpose of the matrix elements. Operators with this property are what we call Hermitian operators. And that's sort of just the whole point of this brief video is to introduce that concept. These are called Hermitian operators. And Hermitian operators have two properties that are very important. One is their eigenvalues are real. And the eigenvectors of those operators form a complete set, i.e. you can use them to form a basis. Any vector in that whole Hilbert space can be described as a linear combination of the eigenvectors of that matrix. And it turns out why they're so important is that all physical observables are represented by Hermitian operators, which makes sense. The results of a measurement, we measure real values. So the eigenvalues are the only possible results of a measurement of a physical observable. So these need to be real. And we've already used the fact that the eigenvectors form complete sets. We didn't really discuss it this way or really even justify doing it, but when we looked at the Stern-Gerlach experiment, we said that a general vector in that spin 1/2 system could be written as a multiplication of the spin up and spin down eigenvectors of our observable. And what we were really doing was saying that we knew that those eigenvectors formed a complete set. Anyway, so that's the big takeaway from this is knowing what a Hermitian operator is, and that all physical observables are Hermitian operators. And this is going to lead to us things. One of the things we're going to use is discuss things like measurement bases. You're going to be trying to think about measuring some certain physical observable, and we can describe any general vector in what we call the measurement bases. So using the eigenvectors of that physical observable to describe our wave function or our state vector.